Good morning, sir.
Good morning. Okay, we can start. So on the group, I've shared the link for last year's lecture notes. Note that these are just the outlines of what was covered in the class. So you may still have to prepare your own notes to document all the proofs and various properties that are getting discussed. And in the same way, I will keep sharing some notes for our ongoing lectures also for number theory. Just a minute, I'll send the link for that. But note that, I mean, in both last year's notes and this year's notes, the number of problems I show in my PDF are quite less. So you have to do some more practice from other sources. So for example, for number theory, I already mentioned Burton as one of the books. But in general, I mean, because we are also studying for Olympiads, so we should also look at past years RMO question papers as another source of study material. So at some point, maybe my plan is in the next 4 to 6 weeks, we would probably cover all the basic theory in number theory that we require to solve RMO and INVO level problems. So at that point, we will start to go through all the past RMO question papers systematically and look at all the number theory questions. And what we would like to do then is, as I said last time also, that we want to look at all the properties as problem solving tools. So we should get an idea of which tool is applicable in which context, and so that that knowledge is going to be very essential to solve new problems. Okay, so I just posted a link on WhatsApp group, which is the folder where I'll keep uploading this year's lecture notes. So okay, can you see my screen? Okay, so just to go over some of the points that we covered last time. So I think well-ordering principle and mathematical induction. A couple of points which maybe I would like to add to what we already discussed last time. So one thing is that yeah, so the well-ordering principle, as we stated it, every non-empty set of non-negative integers contains the smallest element. So there are multiple ways to apply this in slightly different ways. So for example, one sort of variation of that is called the infinite descent. So that is just taking the well-ordered principle and reversing it in some sense. That so by the way, you can do this for any statement. So if there is some statement which says if A is true, then B is true. So then you can talk about what is called the contrapositive of that statement, that if the conclusion is false, if B is false, then the assumption, that is A, should also be false. So in that way, what is infinite descent? It is saying that if there is some non-negative set of non-negative integers which does not contain a smallest element, then that set has to be empty. So if there is some set where if you take any element of that set, let's say K, then you can always find another element which is even smaller. Then clearly you can imagine that in like non-negative integers, this chain of finding the next smallest integer, this has to terminate at some point. So the only way this can happen is that the set has to be completely empty. And this is actually a quite useful trick in solving various problems. So here I also given, so the first problem you can try to solve using this method, okay, infinite descent. And you'll find other problems also. In fact, later when we do Pythagoras theorem, we are going to come across one example of this also. In fact, when we do a case of Fermat's theorem. But there are a couple of other ways of also applying the well-ordered principle. So, for example, one well-known property, Archimedean property. In fact, this is true not only for natural numbers, but for larger sets such as rationals and real numbers also. But again, it's quite obvious that for any pair of AB, you can always find a multiple of A which is greater than or equal to B. And in the second case, you can find the power of A which is greater than or equal to B. So again, basic notions, but in order for us to practice how to apply well-ordered principle, these are good ideas. And induction is, I think, already we have covered. So I think before we start, so I want to cover divisibility, division algorithm, GCD, and all those things today. But before we jump into all of that, just to give us more practice on induction, let us do one question. So, so question 3: prove that every positive integer can be uniquely expressed as a sum of distinct powers of 2. So this was in fact the last time's puzzle at the end when I was talking about binary numbers. That is when I had expressed this property that any number can be written as the sum of powers of 2. So that's actually a good exercise to try and prove using induction. So I'll suggest let's take the next few minutes and everybody try to prove this using induction.
Sir, can you show the question?
Yeah, sure. Maybe I'll just write it. So I want to prove that any natural number can be uniquely from so the important word is uniquely represented. So not only that every number can be written, but there is exactly one way to do it. And important to say, when I say uniquely represented, of course, reordering is okay. So I can write 6 as 4 plus 2 and 2 plus 4. We consider that to be the same solution. So these are not considered different representations. So sometimes in some books you'll find it says unique up to reordering or up to rearrangement or something like that. So to make it clear that rearrangement of the terms is not considered as a new representation. And in particular, I want us to try and use induction for this.
I have an idea.
Yes, Anushka?
Yes, sir. So we can see then when we start with the base case, which is 1.
Wait. Let everybody try. So I'll give 2 minutes for others to try also.
Okay.
But also for those who are able to solve this question, I mean, maybe you can see how to do it, but I would also suggest take the next few minutes to write it properly. So if this were an exam problem, then how will you write the base case, the induction step, and how do you give the logical reasoning at every point? So that is also important. So first question I want to ask for those who have already done this question. We know 2 versions of induction, right? One is normal induction and one is strong induction. So which one do you think we should use here?
Normal induction.
Normal induction?
It's strong.
See, what is the idea of using induction? That I want to use the smaller problem to solve the bigger problem. So if I know how to uniquely represent n as a sum of distinct powers of 2, can I use that information to construct the answer for n plus 1?
Yes.
I'm surprised because in general, if you look at how we wrote binary numbers last time, right? The representation of n doesn't have any direct connection to the representation of n plus 1, right? The representation of n plus 1 can be completely different. So it is not like you can take the representation of n and make just one small modification to get the answer for n plus
1. Sir, what I was thinking was that if we can add 1 and unless we have a distinct power of 2, then the previous one we can just go on combining those 2.
Okay. So yeah, basically I mean
It's
how
the same.
carry over in addition. That is what you are trying to do. Kind of. Okay.
Sir,
Yes.
Like 1
so we
plus
could do
2,
it.
then is already present in 2 plus 4 and so on.
Okay. Gaurav, you are saying something?
Yes, sir. So I was saying that if we know, if we can represent n as in terms of powers of two, we can
Mm-hmm.
represent two n in terms of powers of two, and then we can go on doing it.
Oh,
Sir, I had another idea.
yes, tell me.
So like we can use strong induction and then consider two cases.
Okay.
N plus one is even and n plus one and n plus one is odd.
Okay.
So if n plus one is even, we know that n plus one would be greater than n plus one over two.
Okay.
But since we are applying strong induction, n plus two can be n plus one over two can be written as a sum of distinct powers.
Right.
Now, if
Okay.
we multiply this whole result by two, then n plus one can be written as a sum of distinct powers.
Okay. So
And
only
if
slight problem there. I mean, I think your approach is good to show that it can be represented
yes,
in some way, but whether that representation is unique or not, because it could be that there could be two different ways of writing the same number as powers of two, right? So I think what you
yes,
have proven is the existence part, but not the uniqueness
yes.
part.
In the uniqueness, I think we can show it by a different, easier method. Like what we
Okay.
can assume that there are two representations, and so in one of we consider largest number which is present in one of those but not in, and so then the previous in which if in the it is present in A representation and not in B representation, then
Okay.
the other numbers in the B representation can't add up to A.
Actually, I couldn't hear the last part.
Like
So how do you show the counter example or a contradiction over there?
yeah, so if I'll just show an example. Like if 8 is the largest number which is present in A but not in B,
Okay.
then like to bring them together, the best case can be B has 1, 2, and 4, and A has nothing after that. So, but still, like we can use the 1 plus 2 plus dot 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 till 2 raised to n is 2 raised to n
Okay.
plus
No,
1
I,
minus 1.
I,
So
I don't know. Maybe your
that in that
approach
way we
can
can show
be
that B
made.
is always less than A.
I mean, I don't know if your approach can be made rigorous to cover every possible case. So can you do one thing? Can you, if you have written your solution, you can send it to me. I'll take a look because that would
Sure,
be
sir. I'll just
interesting to
write it
know.
after the class and share.
Yeah, sure. Uh, so this is how I am looking at the question. But Anushka, you have any other idea or something similar to what others have said?
So I had the same idea that we'll first start with so basically this one, and then
Okay.
see that it can be represented with as 2 to the power 0, and then for any n numbers it can be represented. We assume that, and then for n plus 1 we'll say that we are adding 2 to the power 0, and to prove that it will be distinct powers, if we have two same powers we can just combine them to form the next, like if we have 2 to the power 1 and 2 to the power 1, we'll get 2 to the power 2. So like that.
Okay. And what about uniqueness?
Sir, I'm not sure of that.
Okay. Okay, fine. So I think there are some good ideas here, but always the question is in any question like this, or particularly in combinatorics, right? You have to make sure that logically what you think is correct, but can you prove it mathematically in all cases? So how you represent your argument is very important. So when I think Arnav or even Anushka or others said that we can combine the powers to make it larger and larger. So at some point maybe that process will stop, or what if it does not stop? So there are things like that to be considered. So I would suggest a completely different approach, but I'm still interested to know if you are able to write your approach properly with all the logical justification. I would like to take a look at that. Okay, so do try to write it and send it across on the. You can send it to me directly, or you can put it on the WhatsApp group so everybody can take. But this is how I would suggest that we can phrase the problem. So first thing is I want to use strong induction, particularly because as I said, see, if you use induction, then the sort of the representation of n. I mean, I would say that you have to do a lot of adjustment from the representation of n to get n plus 1, right? Like as combining the carryover and all of that. But if you use strong induction, then there is a much easier way to go from the previous representation to the next one. So therefore, I'm going to use strong induction. So So the base case is of course n equal to 1. So there's nothing to be done because 1 is simply written as 2 raised to 0. And I mean, this is kind of trivial that this is unique also because any other power of 2, like 2 raised to 1, is greater than 1. So any other power of 2 cannot be used also here. So base case is fine. So now induction step. Let all of 1, 2, 3 up to n satisfy the property. In fact, let me write n minus 1. Just so that my notation is easy to do. So then I have to prove that n also satisfies the property. So in fact, this is where I'm going to use the one of the properties I had shown in the sheet. So Archimedean principle, right? So if you look at point number 4 here, if I have any a and b, then there exists a power of a which is greater than or equal to b, right? So this is the Archimedean property, and in fact, I mean, slight variation of this we can claim over here. So this n is there. I think I'll leave this as an exercise for you to prove using well-ordered principle or any other way. But I think you can agree that there exists some integer k such that n is precisely caught between the powers of k and 2k plus 1, 2 raised to k plus 1. Does everybody agree with this claim? That such a power, I mean, the powers of 2, like 1, 2, 4, 8, they keep on going up to infinity. So n has to be caught between one of these ranges. And note how this is a semi-open interval. So it is closed on the left side and open on the right side. Okay, so I hope everybody agrees that such a k will exist, but it would be interesting for you to try and prove this using well-ordered principle. Okay, it's not that hard.
This does not hold for.
Sorry?
Sir, this does not hold for n is equal to 1.
Oh, but because we are applying induction step, so it is assumed that n is greater than 1. The induction step always starts with the next term, right? And it all holds true for 1 also, right? Why not?
No, sir. If then 2 raised to 0, then k will belong to non-negative integers, not natural.
Okay, yeah, that is fine. Yeah. No, but I think what I'm saying is that anyway we can assume n greater than 1 because we're applying induction step.
Yes, sir.
Okay. But yeah, good point. Maybe then if you want to include 1 also, I should allow the set of integers with 0 or natural numbers with 0. Okay. So then what can you suggest? What should be the next step for us?
We write it as 2 raised to k plus some number.
Correct. Because if you observe anytime, like if you look at the first few binary numbers that we wrote, always the largest power of 2 that comes before that number is always a part of that representation, right? So therefore 2 raised to k will be part of the representation of n. So if n will be 2 raised to k plus something, correct? So let that something be equal to m. So let m equal to n minus 2 raised to. So now do you see that now we can apply the induction hypothesis. So the fact that 1, 2, n minus 1 are given to satisfy the property can be used here now. So we know that m can be represented as some 2 raised to k1 plus 2 raised to k2 plus 2 raised to kr for some distinct kr.
Sir, shouldn't we make cases if n is equal to 2 raised to k or n is not equal to? Because if n is equal to 2 raised to k, then we get m is equal to 0, for which we haven't said anything.
Yes, I think you are right. So I think if m is 0, then we have to handle this differently. Yeah, good point. Let me just move this down. Yes.
Sir, if m is equal to 0, then we have no need to do that because it is already
Yes.
represented in a power of 2.
Yes, that's true. But it's important that we write. I mean, because we want our argument to be complete, we should make note of that. So So if m is equal to 0, then n is itself a power of 2. So n is equal to 2 raised to k. So here we have already showed that we will do this in 2 steps, by the way. We first only show the existence of the representation, and we'll come to the uniqueness later on. Okay. So case 1, if m is equal to 0, then n equal to 2 raised to k is a valid representation. And case 2, if m is greater than 0, then what we can say is m can be represented in this way. Okay, so now you see how to use the representation of m to come up with the representation of n. So n will be 2 raised to k plus m. So that will be 2 raised to k plus the existing, like the same thing. Okay, so does everybody agree that with this we have proved the existence of a representation for all natural numbers, right? Because we have done the base case and we have showed the induction step also. Okay, so therefore all positive integers have a representation. Yes, Raghav.
Sir, but like what if m is greater than 2 to the power k? Can we show that m is smaller than 2 to the power k? Because if m is greater than 2 to the power k, then 2 to the power k will come in the representation.
If n is greater than 2 to the power k, then n will be greater than 2 to the power k plus 1.
Yes, I mean there are two aspects to it. Firstly, what Arnav says is right, that if m is greater than 2 raised to k, then n was already greater than 2 raised to k. So then n cannot be in this range, right? N will have to be greater than 2 raised to k plus 1.
No, so I'm saying if m is greater than 2 raised to k.
N is equal to, yes sir. So n is equal to 2 raised to k plus m. And if m is greater than 2 raised to k, then then therefore 2 raised to k plus 2 raised to k is 2 raised to k plus 1. Therefore n has to be at least 2 raised to k plus 1. Therefore it won't be in the range itself.
Oh, okay.
So the fact that here n is trapped between this particular bounds, right, 2 raised to k and 2 raised to k plus 1, forces that what is the remainder of, basically out of n we have taken up 2 raised to k away, and whatever is remaining has to be smaller. So that is one point. And second point is assuming that even if that were not the case, then there is still no problem, right?
Yes.
Yeah.
Thank you, sir.
So yeah, I think the point you are raising is important because we are claiming this, all of these are distinct. So I think that is also one thing I should mention here, that I mean, we have shown that n can be written in this way, but what's important is that already k1, k2, k are distinct, but we can also say that also k is not equal to k1 ki for any I. So that was the important point, because m is less than 2 raised to. Actually, that's an important point. Otherwise, we are not guaranteed that all these k, k1, k2 we are distinct, right? So the only reason they are distinct is because m is less than 2 raised to. Okay, so now this was the proof of the existence, but what about uniqueness? Can you see how to use induction for uniqueness also now? So let me clarify that this was only for existence. So this was like part 1. Okay, now let us come to part 2, to the uniqueness. So again, we are going to use strong induction.
Just want to clarify one thing. We have written m is equal to 2 to the power k1 plus 2 to the power k2 till 2 to the power kn. So that is by our induction step, right? Induction hypothesis.
Yes, this is because of the induction hypothesis.
Yeah.
So here you can write by the induction hypothesis. M can be written in this way. So the induction hypothesis gives us this information that any number smaller than n already satisfies the property.
Yes.
So to prove uniqueness also we will use strong induction on n. But before we do that, we will use a small lemma. So sort of a lemma. So let n be represented as so let n be represented as a sum of distinct powers of 2. And for convenience, let me order those indices in decreasing order. So k1 greater than k2 greater than kr greater than equal to 0. Okay. So they are all non-negative indices and order in decreasing sequence. And let k be the integer such that, or the non-negative integer, such that n is trapped between 2 raised to k and 2 raised to k. Then what can you say? What can be the connection of this k and this k1, k2, kr?
There exists a k such that k equals ki, or k1 is equal to k.
K1 is equal to kr, right? So then basically what we are saying is that whatever is the largest power of 2 that comes just before our number, that power must necessarily be included in the representation. K1 is equal to k. Okay, does everybody follow the statement? What is the lemma that we are claiming? That let's just give you an example. If we are, let's say we are trying to represent 60 as the sum of powers of 2, then the largest power of 2 that comes before 60 is 32. So our claim is that the representation of 60 must include 32 as one of the terms. (32 plus whatever is). So can you see how to prove this lemma? Maybe I'll just give everybody a chance to try. So next couple of minutes, just think about how to prove this lemma. Okay, so in fact, do both parts. So see how to prove this lemma, and then do you see how this lemma can be used to solve the uniqueness problem? Okay, so any suggestions how we can prove this lemma? Yes, Raghav.
Yes, sir. So we know that K1 can't be greater than K, because if it is greater than K, then that would mean that uh, then 2 to
Yeah,
the
that
power
cannot
K.
happen. Yeah, correct.
So now we have to consider the case that K1 is smaller than K.
Okay.
Now the maximum sum in K1 is smaller than K would be 1 plus 2 plus 3, sorry, 1 plus 2 to the power 1 plus 2 to the power 2, all the way to 2 to the power K plus K1 plus 1.
Correct. Correct.
Yeah. So if
Yeah.
you take the sum, it would be 2 to the power K1 plus 1, 2 to the power K1 minus 1.
Yes, correct. So basically, if we add up the GP, we'll get a number which is smaller than n. So which is not
N.
possible. Correct.
Yes.
Yeah. Does everybody follow this approach? What we are trying
Yes,
to
sir.
do? That if we don't use that largest power of 2, then even if you use all the other smaller powers of 2, we can never reach n. So that is the contradiction. So
So
is
I
it
didn't
possible?
quite understand his method.
So what he's saying, suppose let's take the example that we're talking about. That is, let's say we are trying to write 60 as the sum of powers of 2, right? And our claim is that we have to use 32. So see what happens. Suppose you decide not to use 32. So then what are the other powers of 2 you can use smaller than 32? So you can use 16, 8, 4, 2 and 1, right? But now see what happens if you add all of them. So in the sort of best case scenario, if all of them are also included, still the total will be smaller than 60. Do you see that? Because the sum of all of them is 31 only.
Yes.
Yeah.
So yeah, so we can just convert this example into the more general formulation. So if possible, let K1 not be equal to K. So as I said, first thing is clearly K1 has to be less than K, because uh, since if K1 is greater than K, then it will mean that n is itself n which is greater than 2 raised to K1 will be greater than 2 raised to K. Oh, sorry.
Sir, greater than equal to 2 raised to K plus 1.
K plus 1. So maybe then K1 is greater than equal to 2 raised to K plus 1.
No, sir, K1 greater than equal to K plus 1.
Oh, sorry. So therefore n, which is 2 raised to K1 plus something something. So n will be greater than equal to 2 raised to K1, which is itself greater than 2 raised to K1 K plus 1, which is a contradiction.
I didn't understand the second step.
This one?
No, before that, like you've written K1 is less than K since K1 is greater than K.
Oh, sorry. So I am claiming that this is true. So maybe I won't write this. So if K1 greater than K, then what will go wrong? Okay, you want to show that K1 greater than K is not possible. So if K1 is greater than K, then clearly this representation of n will force n to be quite large, and n will be greater than 2 raised to K plus 1. So therefore we are saying that this is not possible. So
Yeah, so n
therefore
has to be less than
less than K. Okay. Therefore K1 is less than K. Now, but if K1 is less than K, then the problem is the sum. So 2 raised to K1 plus 2 raised to K2 plus 2 raised to Kr. This sum will be clearly less than or equal to the entire GP. So 2 raised to K1 minus 1. Okay, does everybody agree that basically whatever terms are missing in this GP, I can add them and write a whole series. And everybody knows how to find the sum of this, right? This will be 2 raised to k1 plus 1 minus 1. And but this was equal to n. So if k1 is less than k, which means k1 can be at most k minus 1. So therefore, this whole sum can be at most 2 raised to k minus 1. So then what we are getting is again n is too small now. So therefore, n is less than 2 raised to k minus 1, which again contradicts. So therefore, we are forced to conclude that okay, does everybody follow the proof, the outline of the proof?
Sir, I didn't get that 2 raised to k minus 1 step.
Okay, so see, basically, if k is small, k1 is smaller than k, and because we are talking about integers, so the next smaller integer below k is k minus 1. So k1 has to be less than or equal to k minus 1. Now the representation of n, which is already given. So what we do is we add what are the missing terms and get the full GP over here, and
Yes,
the value of the full GP is 2 raised to k1 plus 1 minus 1. And oh sorry, oh I should have read. Oh okay, sorry. So then because k1 is less than or equal to k minus 1, or which is the same as k1 plus 1 is less than or equal to k. So therefore this is less than or equal to 2 raised to k minus 1.
Yes.
Yeah,
So when you're writing is less than or equal to 2 to the power k1 plus 2 to the power, that is k1 minus 1, right?
sorry, which line?
Above the one you were explaining to girls.
This one?
Oh, yeah, above that.
About. So what is your question?
So we have written, we have just made a representation as 2 to the power k1, and we have written that as 2 to the power k1, and 2 to the power k2 is written as 2 to the power k1 minus 1.
Yeah, correct. No, it's not just that. So the thing is, may not be k2 is 2 to the power k1 minus 1. What I've done is, whatever are the missing terms, those are filled up over here. So maybe they are consecutive, maybe they are not consecutive. So we don't know that. So I'm not saying this is equal. See, this is a less than or equal to sign. So it is not that k1 is k1, k2 is k1 minus 1. It is not a one-to-one correspondence.
Okay.
So like just to give the example of suppose we are talking about some concrete number like 10. So 10, which is 2 raised to 3 plus 2 raised to 1. So this is less than all the middle terms added. So 2 raised to 3 plus 2 raised to 2 plus 2 raised to 1 plus 2. That's what we are saying.
Okay. Got it.
Okay, so I hope everybody's understood this lemma. Yes.
This is a bit about notation. I forgot to ask last lecture. What is the full form of that QED?
Oh, it is a Latin word. I think it means quod erat demonstrata. Basically, it means hence proved.
Okay, sir. Okay, sir.
See, quod erat demonstrata, which is what was demonstrated. Whatever. Basically, hence proved. You will find this quite often in textbooks and.
Okay, sir.
Okay, so then if we have understood the lemma, now do you see how we can use the lemma to prove the uniqueness of our original problem?
Yes, sir. We say that the largest power before n has to appear, and then m is less than or equal to that. And
Correct.
so by strong induction, m has a unique representation.
Yes. Okay, so what we can do is again, if possible, again the base step we already done, so I will ignore that. But look at the induction step. So, so for the induction step, again we can say that given all the numbers 1 to up to n minus 1 have a unique representation. Now for n, if possible, let n have two representations. So let n be given as maybe 2 raised to a1 plus 2 raised to a2 plus 2 raised to ar, where these a1, a2 are all decreasing. And this also be equal to 2 raised to b1 plus 2 raised to b2 plus some 2 raised to bs, where b1, b2, they are also decreasing. So if possible, let these two representations be there. We want to claim that these a1, a2, ar and b1, b2, bs, they are equal. And so now by the lemma again, so if k is that particular integer such that n is trapped between the powers of 2 raised to k and 2 raised to k plus 1, then by the lemma, by the word lemma means branch. I think in some, again I don't know, Greek or Latin some word. So the word lemma means there is just a side result which we did before the main result. Okay. So and in some problems you may have to do multiple lemmas. So there you will have lemma 1, lemma 2, etc. So by the lemma, what can we say that the highest power, so this a1 and b1, they are both going to be equal to k, correct? So k will be equal to a1 and b1. So therefore we can consider n minus 2 raised to k. Okay. So n minus 2 raised to k will be, again this will have both the representation. So instead of starting from a1, we'll start with a2, right? So 2 raised to a2 plus 2 raised to a3 plus 2 raised to ar, and this is also equal to 2 raised to b2 plus 2 raised to b3 plus 2 raised to bs. Okay, and now do you see the contradiction that by the induction hypothesis, n minus 2 raised to k was supposed to have a unique representation. So, but n minus 2 raised to k by the induction hypothesis. So I think last time I did not introduce the term induction hypothesis. So the induction hypothesis refers to the whatever you are assuming for the induction step. So in this case, what we are assuming is that 1, 2, n minus 1, they are all have a unique representation. Okay, so that is what we call the induction hypothesis. So if the representation of n minus 2 raised to k is unique, which forces all of these terms to be equal, right? So therefore, a2 is equal to b2, a3 is equal to b3, etc., and ar is equal to br. So therefore, n minus 2 raised to k has a unique representation, and therefore n also has a unique representation. So I guess again the only case where this proof will not work is same thing what Arnav pointed out in the previous case. What if n is itself a power of 2? Then what happens? So that's just a one corner case.
Then we get a1 is equal to b1, and that's just 2 raised to k and 2 raised to k.
Yeah, correct. So basically there is no additional terms in the expansion anyway. So yeah, that's just a minor point we need to take in mind. Okay, but so I hope that this give you an idea that how you can use induction, and particularly strong induction, to solve a problem. So this was the question 3. So I'll leave the others as exercise for you to try, and you have many more problems from Burton which you can also try. Okay. So with that, I would like to move on to.
We have to try the others for homework.
Yes, you should try them. Correct.
Okay, sir.
In particular, I think first and second are quite easy. The fourth one, I'm interested to know if you can write it properly. So, but for that, I'm assuming you already know what is the inclusion-exclusion principle. Has that been covered in your combinatorics lectures? Or if not, then maybe you have to wait until that is done before you try that problem. Okay, so this was all of this induction and well-ordered principle. I would say that was like the foundation of integers, so to say. But now we'll come to the more sort of the meat of the matter, where most of the number theory actually happens, which is divisibility, remainders, things like that. So that is what we'd like to get started with. So
And we have to try to prove that n can be trapped between the two powers of two of our homework.
yes, not only that. In fact, I mean, in this well-ordered principle, you see that both Archimedean property and in general for any base A, the same property holds true. So
Yes, sir.
you should try to prove both of these.
Okay, sir.
Okay, so so let's begin with the sort of the most fundamental theorem, which is the division algorithm. Which I think in school we just kind of assume that whenever you divide a number, you will get a quotient and a remainder. But two aspects. First is why should that always be the case, and then secondly, why should that quotient and remainder be unique? So that is what the division algorithm claims. That if you have any two integers a and b, then there exist unique integers q and r such that a is equal to qb plus r, and because r is the remainder, it has to lie between 0 and the divisor. And I don't know how this term came. So the word algorithm, if you know anything about, I mean, typically is used in computer science to refer to like your sorting algorithm. It's a procedure to accomplish something. Division algorithm is not really an algorithm in that sense. It is a claim, but for some reason it got the term algorithm. I don't know if there is some history to that. I mean, to be honest, if you ask me, this is such a fundamental fact. I'm sure this was discovered long before there were computers. So then why was the word algorithm added there? I don't know. So if A and B are integers, oh, and I think it will be the fancy. Then there exists unique. So by the way, again, just notation. So I think last time I mentioned that this is a symbol for there exists. And when you have exclamation mark, it means unique. So there exists unique Q and R. Such that so how can you try to prove something like this? So, I mean, to be honest, this initial part of number theory can seem quite boring because we are proving things which we all kind of know to be true already. So, what is there to be proved in that? Might be the feeling that some people may have.
Sir,
But
I know this proof.
you already know this proof. Okay.
Yes, sir.
Then we'll let others a chance to try and discover
Yes,
the proof. But I mean, the point I was making was that why are we spending so much time in this initial sort of foundation of number theory? The reason is that we want to develop our own mathematical rigor. Two aspects to it. One is to develop the rigor so that later on when we come across more complex topics, we know what is the right logical approach. So we need to be sure about that. And there is a second completely different aspect to what we are doing here, which we don't have enough vocabulary to talk about that. But if you come across topics such as group theory, rings, and field theory, turns out that a lot of properties which are true for integers are also true for those higher order structures such as rings and fields. And in fact, like for example, you already know that there is a division algorithm for integers and there is a division algorithm for polynomials. So you can divide one polynomial by the other polynomial. And is it just a coincidence that polynomials behave like integers, or there is some deeper logical reason why you can treat polynomials like integers? So the whole ring theory is the name of the topic, which will require a lot of lectures to cover, and frankly is out of the scope of Olympiad, so that's why we don't go there. So this is one proof which I know, because I mean this is the proof which I have seen in Burton, and maybe this is the standard approach which most people use. But if somebody has a completely different approach, I will be curious to know that. But in general, what we do is this: we consider the set. So the idea is that I want to come up with all the possible candidates for the remainder. So if A is equal to QB plus R, which means that R is equal to A minus QB, correct? So what if I try different values of the coefficient? So 0, 1, 2, 3, 4, etc. So if I consider all such possible remainders, and again I only want I don't want negative values, so I only want positive or non-negative values. Okay, so consider this set S, which has all the expressions of the type A minus QB, where the A minus QB is non-negative and Q is an integer. So Arnav, do you have the same approach or something different?
Yes, sir, same approach.
Okay. Yeah, I think everybody has. I don't think there is much room for doing something different. But if you think about it and come across some different idea, let me know. So then clearly this set S contains non-negative integers, and is it empty or non-empty? What can you say about that?
Non-empty.
Okay, but why? I mean, what you are saying is at least one element should exist in S, but why?
If A is non-negative, then we can just input Q equals 0.
Yes. So if A is itself greater than or equal to 0, then A minus 0B, which is A itself, is 0. Therefore, A belongs to this. And if A is less than 0,
So then we can put Q as some negative integer.
but which negative integer?
Then we know that there exists an integer set, let's say Q naught, which is that exists a natural number Q naught, such that B Q naught is greater than equal to greater than absolute value of A by that property of Archimedean property, and then we can just check the negative of Q naught.
Yeah, correct. So you can apply that Archimedean property, or very simply, you can just use Q is equal to A. Do you see that? So A minus A times B. This is also sufficient because this is given B greater than 0. So now in this you will see that both A is less than 0 and 1 minus B is less than 0. Therefore the product has to be positive. Okay. So either way, it's, I mean, this is a trivial point that you can show that S is not. So if S is non-empty and it also it consists of non-negative integers, so what can we invoke? The well-ordering principle, right? Therefore, by well-ordering principle, S has a least element. So that least element we call R, and therefore A is equal to QB plus R. Now we also want to prove that. So two things which are left to be proven. First is R has to be in this range 0 to B. So claim that 0 less than R less than B. Why is this claim true? Because if they are not the case, I mean R greater than 0 is true because that is how we have constructed the set S. But why is R smaller than B? So if possible, let R be greater than equal to B. Then what will happen? we can take away one more copy of B, right? From A. So A was, which was equal to QB plus R, can be written as AB, QB plus Q plus 1 times B plus R minus B. So this term R minus B, which is because R is greater than or equal to B, so R minus B is also non-negative. So therefore it means that A minus Q plus 1 B is also in S. But that's a contradiction to the fact that R was chosen to be the smallest element. So here we are coming up with the term which is even smaller than R, which is the contradiction. Another notation, this is more rare notation by the way, but at least some people use it. This is a contradiction. This hash sign means contradiction in some literature. Okay, therefore R has to be in the range 0 to B.
Sir, here, why did you put exclamation mark? I did not get that.
It's how you write in English, right? It's a statement.
Oh, okay, sir, like no mathematical meaning.
No matter.
I thought that was for unique, so I...
No, it doesn't mean. Okay, so we showed that R belongs to the range 0 to B. Now coming to the uniqueness, that why should this quotient and remainder be unique? So uniqueness. So if possible, let there be two such values possible. So if possible, let A equal to Q1B plus R1 and Q2B plus R2, where both Q1, both R1 and R2, all of them satisfy the same condition. So both R1 and R2 are in the same range. So now what will happen? Let's subtract the two. So we will get 0 equal to Q1 minus Q2 plus R1 minus R2. Or if I just rearrange that, I will get R1 minus R2 is equal to Q2 minus Q1B. Okay, do you see what can be the problem with this statement? I don't know, anybody else? See, because R1 and R2 are both given this range, right? 0 to B. And we are saying R1 minus R2 is some multiple of B. So can that happen? That in the range 0 and close B, by the way, there are two terms which are both multiples of B. Because typically, if you have a multiple of B, the next term, which is also multiple of B, has to be at least B ahead or behind, right? So here, if Q1 and Q2 are not equal, then Q2 minus Q1, the sort of the modulus of this is at least 1. So therefore, the modulus of the RHS, right, the absolute value of the RHS, this has to be at least B. But because R1 and R2 are in this range, so the absolute value of R2 minus R1 can be at most the largest term minus smallest term, which is B minus 1 minus 0. So this is the contradiction, that here we are getting the modulus is less than B minus 1 and here it is greater than equal to B.
Then we should say that then our R2 is equal to R1 is the only solution.
Yes. Therefore, we are forced to say Q1 is equal to Q2. And if Q1 and Q2 are equal, then R1 and R2 will also be equal. Okay, so I hope everybody follows the proof. And see, more importantly, pay attention to what is the writing style. And probably if you look at how Burton writes it, he'll be even more polished. He'll make sure he avoids all the corner cases and things like that. So in any way, this is the writing style you need to be familiar with for Olympiad. Many times, particularly the questions which people have submitted, I see the solutions are there, but many times it is like you just give the outline of the solution, not the explain the full details. Like finally understand that in the exam you are going to write the paper and submit it. You are not going to be there in person to explain your solution to the examiner. So whatever you write in the paper should be enough to communicate all your ideas to the examiner. So write with that intent. Okay? Make everything crystal clear.
So just explain the last step.
Sure. So if A can be written in two different ways, Q1 R1 and Q2 R2, then with these manipulations we get to this step that R1 minus R2 is Q2 minus Q1 times B. So I mean, just thinking about it logically, multiples of B going the difference between any two multiples of B has to be at least B, right? It cannot be smaller than B. And here what we are getting is R1 and R2 are both trapped in the same range 0 to B, which cannot happen. So the absolute value of the difference between R2 and R1, which I am showing on the right hand side, can be at most B minus 1. Whereas on the left hand side, if Q1 and Q2 are not equal, then the absolute value of this RHS is at least 1 times B, which is B. So,
R2, the modulus of R2 minus R1 can be B also, right?
no, because B is not allowed to be part of the set, right? It is less than B. So the largest value the remainder can take is B minus 1.
Oh, okay. Got it.
If B were allowed, then this would be a problem, because then what you're saying is true.
Right.
So in fact, if we allow B, then uniqueness is not true, right? I can divide a number and get two different remainders. Like for example, I can say 10 is equal to 5 into 2 plus 0, and I can also write 4 into 2 plus 2. So if when I divide by 2, the remainder can be 0 or 1. It is not allowed to be 2.
Right.
Okay. Okay, so with the division algorithm done, and in fact, I encourage you to try multiple versions of division algorithm. I think these are exercises given in Burton. For example, I remember one exercise which says that same thing, everything is same. So if A, B are integers, etc., prove that there exists unique Q and R such that only that condition is different. The condition is, I think, like something like this. So this is a completely different range in which R is allowed to be. But again, you'll see that it exactly spans one sort of B level cycle, one cycle of length B. So you can come up with your own division algorithm in that way. Okay. So so now coming to divisibility. So main thing is I think most things follow from the definition of divisibility itself. So that is one of the wonderful things about this topic, that the assumptions are so less and most of it is applying what you know. So if A and B are integers such that there exists some integer B then so this is the notation of divisibility, that if there exists some integer B such that AD equal to B, then we write A vertical bar B, and which is expressed as A divides B, or B is divisible by A. So You can say B is divisible by A or A divides B, the same thing. And important with all definitions, it is always if and only if. So if I'm given that A divides B, then such an integer D should exist. And if such an integer D exists, then A divides B. So probably instead of saying if, then it should be if and only if. But generally in definitions, we write, the style of writing is if something, then we call it so and so. But understand that all definitions are two-way streets. Okay. So based on this, I think you can prove on your own lot of basic results, which I will not do. So if A divides B and A divides C, then you will see that A divides B plus C and B minus C and things like that. So these are, I think, properties which even in school they are covered. But of course, they may not give you the full technical proof of that. But I think everybody is well equipped to write the proofs. One part which I want to highlight in particular is if A divides B and B divides C, then A divides C. So this is what is called a transitive property. Okay. So if A and B have some relation and B and C also have some relation, then you can say A and C have the same relation. This is called a transitive property. Okay, so I hope if I give you enough time, you can prove these things. And in fact, the first statement A divides B plus C and B minus C can be taken much further. In fact, any combination of B and C can be divisible. So in fact, if this is true, then A divides sort of some MB plus NC, where for all integers. So this is what is called a linear combination of B and C. Okay? So if A divides B and C, then A divides any linear combination of B and C. Linear because there is no square term like that. Okay? This is called a linear combination. Okay. And so I also listed all these properties in the document. So when you go through the notes, you will find all of these things and you can try to prove them on your own. Okay. But I want to actually spend some time to discuss what do we mean by transitive property in a more broader context, because this is going to come up again in the when we do congruences. We need to know what we mean by transitive, symmetric, and things like that. So let me just take some time to talk about this three topics: sets, relation, and functions. So if you go to any undergraduate textbook library, like even in Bhaskaracharya Pratishthan, almost any book you pick up, always there is a chapter 0, and the chapter 0 is always given this title, because they are kind of the building blocks of all the mathematics that is going to come. Okay. So already I think set we understand, we consider that to be an undefined term and we'll work with that. But what is a relation and what is a function? So again, I think you already may be using functions in different ways, but it's good to give a proper definition of the function. Okay. So in particular, when we have any two sets, you can talk of what is called a cross product of the set. So given set A and B, we denote A cross B. So A cross B is nothing but the set of all ordered pairs where the first term comes from the first set and the second term comes from the second set. Okay. So if, for example, A is the set of the numbers 1, 2, 3, and B is the set of the numbers 4, 5, 6, then the cross
will be 1, 4, 1, 5, 1, 6, 2,
yeah,
4, 2, 5,
all those. So total will have 9 terms. Okay, that is what the cross product means. Okay, so a relation between A and B is just a subset of their cross product. Okay, so a relation let's say sometimes we use the letter R to denote the relation. And we say that, so if some particular pair belongs to the set R, then we say A is related to B. Under R or by R. And we often write it as A, R, B. Okay. The interesting thing is that R can be any subset of A cross B. So it doesn't have to have any special property. It can be the empty set also. If R is the empty set, then there is no relation between A and B or any two terms of A and B. And R can be the entire cross product also. In that case, every element of the first set is related to every element of the second. Okay, so we just saw an example of a relation a few minutes before, which is divisibility. So divisibility is one kind of relation. So you can say divisibility. Let's say if we decide to denote it by the letter D. So this D is a subset of the Z cross Z. So if you take all the integers and cross product it with all the integers, so this is a infinite set in two distinct directions, right? It has a 0, 0, 0, 1, etc. 1, 0, 1, 1. So like that, and in fact in the negative side also. So this is a very big set of all possible combinations of two integers. And what we are saying is that divisibility set D or the relation D is a subset of this, which only contains the pairs where the first number divides the second number. So for example, D will contain the element. So 1, 2 is an element of D, but 2, 3 will not be an element of D. Like that. But this is a very clumsy notation to write it this way. That's why we often write 1 divides 2 and 2 does not divide 3. But that is just a convenience notation. But at the core of it, the logic we are doing is we are talking about a relation between two integers. Okay. So now any relation, if we come back to the theory once, for any relation can satisfy three properties. Okay. So the three properties which can be satisfied is one is called the reflexive relation. So reflexive means if reflexive means for any. Oh, sorry. Important to say. Here in general, I was talking about two different sets, A and B. But now let us consider the case where it's the same set. For example, here both Z and Z were involved. So it is a cross product of the set with itself. So if that is the kind of relation we are talking about. So let R be a relation between A and A. So in other words, R is a subset of A cross A, where A is some set we don't care about right now. So then R can satisfy three properties. Note I'm saying can satisfy. I don't insist that every relation has these properties, but if they are satisfied, then something we can say. So first is called reflexive. So reflexive property says that for any element of the given set, so for any element of A is always related to itself. Okay? If this is true, then it is called reflexive. So does divisibility satisfy this condition? Is every number divisible by itself?
Yes, sir. It's correct.
Yes, sir.
Yes. So clearly divisibility, which we are denoted by D, does satisfy this because every number is divisible by itself. Second is symmetry.
Which says that if A is related to B, then B is related to A.
Yes.
So this is not satisfied by divisibility unless A is equal to B.
Yeah, correct. So in general, it is not satisfied. In some special case, even if it is satisfied, we cannot say the relation is symmetric.
Shouldn't we say A is equal to plus minus B?
Plus minus B, what does that mean?
No, sir. I think Anushka said that unless A is equal to B, so I was asking
Oh,
if
yes, yes. Yeah, okay. Plus minus b is correct.
Yeah.
So
If
every
you are-
number also divides its negative, right? 5 divides minus 5.
correct.
So this is not satisfied by divisibility. And the third is transitive. So if, I think that you already saw. So if A is related to B and B is related to C, then it implies A is related to C. So this is satisfied again, right? So divisibility satisfies, so they are often shortened as RST. RST. So divisibility satisfies R and T, but not S, correct?
So it is not an equivalence relation.
It is not an equivalence relation. So if there is some relation, so if a relation R, okay, unfortunately the same letter R is coming in both places, but let's leave it for now. If R satisfies R, S, and T, it is called an equivalence relation. Okay. And we'll see examples of this soon. So for example, in fact, in geometry, you already know one such relation. What is some relation in geometry which you already know, which satisfies R, S, and T?
congruency or
Congruency. So let's say let T be the set of all triangles. All triangles in the plane. Then this symbol which we often use is a relation on T or from T to T. There are slightly different ways of writing that. Okay, because you can say some triangle ABC is congruent to triangle DEF and things like that. And I think it's very clear that all of these three are satisfied, right? Every triangle is congruent to itself. If triangle 1 is congruent to triangle 2, then reverse is also true. And if triangle 1 is congruent to 2 is congruent to 3, then 1 is congruent to 3. Even similarity is a relation. Similarity also has the same property. So
Yes.
both congruence and similarity of triangles are equivalent relations. So there is a very important property about equivalence relations. Does anybody know this? Something called equivalence classes, if you have heard of this term. So this is the property, or in fact we can call it a theorem, that if some set S has an equivalence relation R, but that's a very bad way of writing. If there is an equivalence relation R on some set S, then S can be partitioned into subsets Si such that all terms within each partition are related, and no terms from distinct partitions. In other words, you can group all the elements of your original set into these buckets where all the elements within the bucket are all related to each other. So for example, in the case of triangles and congruence, let's say, if let's say I'm talking about this particular triangle ABC, okay, then all the triangles in the plane which are congruent to this ABC, they will all come under one bucket. So basically every triangle shape will go into a different bucket, etc. Okay. So like that, the entire set of triangles can be partitioned into these buckets where all the elements of one bucket are related to each other. So basically, in a sort of a plane, the same triangle can be rotated, reflected, things like that. So all of the triangles which are congruent, they're all going to come in the same bucket, etc. Okay, does everybody understand the intuition of this picture?
Sir, can you take
Yes,
little
sir.
up?
You want me to repeat this?
No, sir, can you take little up this?
I couldn't hear you.
I think he means scrolling up.
Oh, you want me to scroll up? You want to look at this? Okay, so again, just to explain, if there is a equivalence relation R, so equivalence relation means it satisfies R, S, and T, all of them. Then S can be partitioned. So when we say partition, which means that S is a union of all those subsets. So S, suppose these are like countable subset, and S will be S1 union, S2 union, etc. Where partition always means disjoint. So no two elements will be in two different subsets. So S1 and S2 are disjoint, S1 and S3 are disjoint like that. Okay? So you have grouped all the elements together, which are all related to each other. So like that, you basically have formed, like in the class, you know how you typically form smaller groups of students. Maybe all Marathi speaking students will form their own group. All Gujarati speaking students will form their own group, like that. So in that way, all the elements of S can be partitioned into these groups. Okay. Now the question is, why is all of this important for number theory? So and importantly, so these partitions are called equivalence classes. That part I missed to write. So these partitions are called.
And when we will take modulo, I think this would be useful.
Exactly, correct. So the congruence notation is a example of an equivalence relation. So I just wanted to motivate that. So in fact, we are going to do congruences more formally, maybe a couple of lectures down the line, but just to give you a flavor of how that theory is related to relations in general.
So in congruence, equivalence classes are like, if we consider mod say 5, so the equivalence classes are congruent to 1 mod 5, 2 mod 5, 3 mod 5, 4 mod 5, and 0 mod 5.
Yes, exactly. Correct. So yeah, just what Anushka said right now. So let's say we consider the divisor as 5. Okay, so let some divisor be equal to 5. Now consider any two integers. So in fact, the relation I'm talking about, let's define the relation. So we define the relation R5. So it's a subset of Z cross Z, where if I give you any two terms integers, then A is related to B if and only if A and B have the same remainder. One dividing by 5. Okay, and 5 is, of course, there's nothing special about 5. You can do the same thing with any divisor. But this is the relation I'm defining, that if you give me any two integers, if they both of them have the same remainder on dividing by 5, I will say that they are related. Okay. So first thing, can you see that this relation satisfies all the three properties R, S, and T? So the question is, does this R5 have R, S, and T properties?
Yes, sir, because if we consider
Yes, sir.
remainders, we just go to equality, and equality is the equivalence relation.
Yeah, correct. Because see, reflexive means what? Every number is related to itself. So every number obviously has the same remainder on dividing by 5. Then if A and B have the same remainder on dividing by 5, then B and A will also have the same. That's also trivial. And if A and B have the same remainder and B and C have the same remainder, then again A and C have the same remainder. So all of these are obviously yes. So therefore R5 is an equivalence relation. And so under R5, I can split my set of integers into this equivalence class. Okay. So therefore Z can be written as a partition of. So what will those sets look like? So let us take the number 0. So all the elements which are related to 0 will go inside this set. So what are those numbers?
0 plus minus 5 plus minus 10 plus minus 15, so on.
Etc. Let me not write plus minus 5. Instead of that, let's write 0, 5, 10, 15. So all of these are going to be the first equivalence class. What will be the second equivalence class? 1 and all the numbers whose remainder is 1.
-4, -9. Yeah.
And like that. So you see, I'll get 5 different classes like this, where all the elements within one class are related to each other. So if I take any two numbers of the first set, they will have the same remainder divided by 5. And there will be no case where the first class and the third class are related. That cannot never happen, because the remainders are always going to be different. Okay. And as I already said, that there is nothing special in 5. You can do the same thing with any other number. And so instead of this A R5 B is a kind of clumsy notation. Instead of that, the congruence notation is A congruent to B modulo 5. But it's the same idea. Okay. So I mean, I want you to appreciate how congruences are going to be a kind of equality. And many things which happen in equality also happen with congruences. Like just as you can add and subtract equations, you can add and subtract congruences also. So all of those things will happen in the future. Okay, but coming back to divisibility. So understandably, divisibility does not create an equivalence classes because it does not support S. Right? S is not satisfied. Symmetric is not satisfied by divisibility. So it is kind of slightly a weaker property in that sense. Okay. So then the next part which we want to talk about is the common divisor and greatest common divisor. So if there are some integers z, a and b, such that and some integer z, such that d divides a and d divides b, then d is called a common divisor of a and b. Okay, and in general, any two numbers will have several such common divisors. But out of all such common divisors, the largest one is what we call the GCD, right? So among all such common divisors, the largest one is called the GCD of a common. And why would there be a largest divisor? Can it happen that the set of common divisors is like arbitrarily large?
No, because if D is greater than either of A or B, then absolute value of A and B, then it can't divide A or
Yeah,
B.
correct. So this is like one of the exercises which you have to do. So in the sheet, you'll see this particular line. If A divides B, then modulus of A is less than or equal to modulus of B. So what that implies is that in the case we are talking about, if D divides A and D divides B, then the modulus of D has to be less than the moduli of A as well as B. Therefore, there is a sort of upper bound on how large the common divisor can be. Therefore, it's sort of guaranteed that the GCD exists. And obviously, one is always a common divisor of any other.
Yes, sir. So we can say that the set of common divisors is non-empty,
Non-empty.
and there is at least one element present, and the set is finite. So there
Yes,
is
correct.
maximum.
There has to be a largest element. Correct.
Yes.
Okay. And so what you can do is if D is the GCD of A comma B, then I can write A as D times A1 and B as D times B1, where basically once I take out the GCD part, the remaining part A1 and B1 have to be co-prime, correct? Do you see how to prove this?
Yes, sir.
Yeah.
So we have
Because
to prove that A1, B1 are co-prime, right?
yes, correct.
So we can prove a contradiction. I suppose.
Yes, correct. Because if they are not co-prime, then it means you can come with even larger GCD. Correct.
Yeah. So GCD will be like D times the GCD of A1, B1.
Correct. In fact, in general, you can prove this fact that if any terms which you have like AM and AN, like GCD of AM and AN will be equal to 8 times GCD of AM and AN for any numbers AM and.
So like proving, we can just say that let the GCD of A1, B1 not equal to 1. So we
Yes.
have a number k such that GCD such that k divides both A1 and B1, and then we can say that A1 is equal to k times A2, B1 is equal to k times B2, and then
Yes.
substituting the values of A1, B1 in A and B, we'll get A is equal to D times K times A2 and B is equal to D times K times B2. So we can
Yes.
say that the GCD of A and B will not be B, but it will be a D times K, which is a contradiction.
Yes. Correct. Did everybody follow the argument which Anushka
Yes,
gave?
sir.
Yes, sir.
Yeah. And this is a pretty standard. Whenever you something the greatest or the smallest one, this is a typical approach that we try to prove that something even larger or smaller can exist, which is the contradiction. Okay. But there is a very interesting property about common divisors that every given a comma being said and let uh, d be the GCD of a and if I write this in English, it is that every common divisor divides the greatest common divisor. This is something that may be surprising for you. That the GCD is basically a multiple of any other common divisor. So if I were to write this in English, this is what it looks like. But if I were to write it in notation, let D be the GCD of A and B, and let there be another number G such that G also divides A and G divides B. Then my claim is that G divides B. And you can check this with some examples that the GCD is always a multiple of any other common divisor. Okay. So maybe I'll give you some time to try and prove this result.
Sir, should we first prove the Bezoos theorem or without that we can do?
I don't remember actually. Let's try. I mean, see, the thing is, if we get stuck, then anyway we'll do Bezoos theorem and come back to this one. But if we can do this without Bezoos theorem, that would be interesting. I honestly don't remember right now.
I got the proof.
Okay.
Sir,
I also got the proof, but I am a bit puzzled that. So, Anushka, you have proof? Arnav, you also have a proof?
Yes, sir.
Yeah, I'm hoping there is no flaw in my proof, but I'm a bit surprised that. Okay, maybe Anushka, can you give us your idea?
Yes, sir. So first I started with so D is the GCD of A1, A1, A and B. So
Okay.
A is equal to D times A1 and B is equal to D times B1.
Yes.
Where the GCD of A1 B1 is 1.
Yes.
So we now let us keep now we'll go to G. So we have got the G divides A and G divides B. So
Yes.
let us say that A equals to G times A2 and B
Okay.
equal to G times B2, where
Okay.
where the GCD of A2 B2 may be greater than equal to 1.
Yes, correct.
So case 1, when A2 the GCD of A2 B2 is 1, then
Okay.
this would mean that G is the GCD of A and B. So
Yes.
G is equal to D. So
Yes.
which would mean that G divides D.
Yes.
Then if the GCD of A2 B2 is greater than 1, we'll
Yes.
consider it to be K. So
Yes.
A2 is equal to K times A3 and B2 is equal to K times B3. And over here we get that A3 B3, the GCD of A3 B3 is 1. So we
Yes.
get A is equal to G times K times A3 and B is equal to G times K times B3.
Sorry,
Where,
can you repeat the last part? A is equal
yeah.
to?
A is equal to G times K times A3
Correct.
and B is equal to G times K times B3.
Yes.
So we get that the GCD of A and B is G times K. So G
Yes.
times K is equal to D, which means G divides D.
Yes, correct. But I think in this we may have inherently used the inverse of this.
Yes,
So,
sir. Converse.
yeah, converse, sorry. See, here this particular property where we said if D is the GCD of A and B, then D and you take away D, you get A1 and B1, where the GCD of A1 B1 is equal to 1. The converse of this would say that if there is some number G which divides A and G divides B, and the sort of the remainder after you take away G is equal to 1, then G is the GCD.
Yeah.
So this is the converse of this statement, which we have not technically proven. So if we can prove this independently, then I think your proof is complete. But that maybe we have to give it some more thought. Okay. But yeah, if you assume this converse, then I think your proof is complete. So Arnav, you have any approach which does not require this?
Sir, I use prime factorization.
Prime factorization. Okay, but the thing is that itself makes a lot of assumptions. So it is like we are using something more complicated to solve something simpler.
Yes, sir.
So I don't know about that also. So I have a proof which does not require any such thing, but I am not confident that my proof is correct or not. So let me maybe I'll just write what I have and as a food for thought, and if we can see if it is correct or not, we'll try. So if possible, so my proof is by contradiction. So if possible, my claim is that G should divide D. So let be the case that G does not divide D.
Yes, sir. I'm trying by the same thing.
Okay, so my idea is we'll write D as the quotient plus remainder. Where now what I can say is the remainder is greater than 0 also. Sorry. Unfortunately, my handwriting makes it difficult to say which is Q and which is G, but I hope everybody follows. So, and now kind of the same start which Anushka gave us, that if A is equal to DA1 and B is equal to DB1, where A1 and B1 are co-prime. Okay, and G I will not use immediately, but if you just in this itself, if you substitute D, what we get? A is equal to QG plus R times A1, which I can expand as A times Q times G plus A1 times Q times plus A1 times R, and B is equal to QG plus R times B1 is equal to B1 QG plus B1 into R. Okay, and in this, I think what I am trying to use is that I know that G divides A and G divides B. So in this, LHS is divisible by G and this term is divisible by G. So therefore, this term is also divisible by G, correct? So therefore, I get G divides A1R and similarly G divides B1R. And now from here, I think some contradiction should arise, because see what's happening. A1 and B1 are co-prime. So there is, I mean, I'm going to use the word prime factor, which are not introduced here, but intuitively speaking, before I write the proof, A1 and B1 don't have anything in common, right? So G cannot divide A1, so G has to sort of divide R. But if G divides R, then this condition cannot be true. R is less than G. So something is going.
Why does G does not divide A1? Because
I mean, what I want to say is that whatever prime number, that's why I mean that I'm a bit hazy to say that my proof is technically correct. But if the prime number, if G is greater than 1 and there is some prime P which divides G, then that same prime has to divide A1 also.
no, sir. Yeah, no, sir.
Oh, no, yes.
Divide R also, right? Because
yeah, it can divide R also.
Yes.
So I'm see what the sort of intuition which I'm trying to say is that
So G cannot divide R for sure, but exactly the thing that G cannot divide A1 is not really coming up, because A1 may not necessarily be prime.
We are not able to relate G to A1.
Yes, sir.
Correct. Sir, we have to arrive to a conclusion that R is equal to 0. But we don't get anything from this.
no, if we get R equal to 0, then that's exactly what we want, right?
Yeah.
But I'm not able to get there from here. Okay, maybe give it some thought, and maybe possibly if this solution cannot be completed, then as Arnav said that we'll have to first do what is called Divisor's theorem, which I think that also indicated in this sheet. So this point 4 is the Divisor's theorem. We can do that, and then we have to come back to this maybe. So we'll see if we can do this without Bisort's theorem, that will be quite interesting, because then I think we would have come with a quite original and non-standard proof. Otherwise, pretty much every textbook does it that way. So maybe we'll give
Can we
some
find a way to prove the converse of this and then use a proof divisor?
converse. So what would be the converse exactly? I think converse is obvious, right? Any factor of the GCD is going to be a common divisor anyway. That part is kind of
The
obvious.
converse of the theorem we are proving.
Oh, I mean, you are saying that this one?
Yeah.
So if you can prove this converse also, then we are done. But that also might turn out to be as hard as the problem we are trying to solve. I don't know. So, but anyway, give it a try. If you get something, let us know.
So can we maybe try linear combination in some way?
So the thing is, what we already showed earlier is that if if A divides B and A divides C, then A divides any linear combination of B and C. That is the easy part. The reverse we have not proven, which is actually what Bisort's theorem says, that if you consider all such linear combinations of B and C, that entire set itself is divisible by the GCD, and in fact GCD is the smallest element of that set. So that is the Bisort's theorem, which we are yet to do now. But anyway, so, yes, go ahead.
Sir, for the for your method of proving this thing that uh, G divides D, sir, so we arrive to this. So we know that G cannot divide R because R is less than G.
Yes.
And sir, we know that A1 and B1 are co-prime. So
Yes.
therefore, by this methodology, therefore, if G divides A1, G cannot divide B1.
Yes, correct.
So because they cannot have any common factors, so
Yes.
therefore if G divides A1, G cannot divide B1.
Yes.
So therefore in the second case, G should divide R, but it cannot
but
divide R in
no,
any case. Therefore we
that
come
is-
to
Right,
contradiction.
you're almost right. The problem is that is not exactly true. So if in the second statement, right, if G does not divide B1, that doesn't necessarily mean G has to divide R, because see, G can be split into two different parts. One part is divisible by B1 and one part by R. So those kind of things happen. So I mean, to give an example, like for example, 6 divides 18, but 18 is nothing but 2 into 9. But because 6 does not divide 2, can we claim therefore 6 divides 9? That's not
Okay,
right.
because
yes.
their
I think I
GCD is
got one of the proofs. I think I got an idea about this.
I mean, even intuitively I feel something can be done here, but I think we need some time to clean it up and see if we can.
Sir, we can consider maybe like since G does not divide R, we can say that the GCD of G and A1 is not equal to 1.
Okay.
And since GCD of A1 and B is equal to 1, we can say that GCD of G and B1 is equal to 1.
Okay.
And so then in the second equation, G divides R, which is a contradiction.
Yes, sir.
Wait, I think even there might be some flaw. Can you repeat the steps again?
Yes, sir. Since R is less than G and
Yes.
greater than 0, G does not divide R.
Yes.
So GCD of A1 and G is not equal to 1.
GCD of A1 and G is not equal to 1. Why?
Yes, sir. So
No. Why is this true?
sir, because if GCD of A1 and G is not equal to 1, then I don't remember the name, but by some there is some, I'm not sure about the name, but then G divides R.
So I think that Euclid's lemma actually. Yes.
Yes, sir. Euclid's lemma or something like that.
But I'm afraid I don't know if Euclid's lemma requires this property. Then we are in a circular loop again. So
Oh,
maybe that can be done. In fact, I actually want to use Euclid's lemma for this. So maybe first step we have to prove Euclid's lemma and then do this. Maybe that is how.
yes.
But anyway, maybe I'll need some time to work out the details, and we are almost out of time. So I will. Everybody, we can try this in our own way and see if we can get any progress. And if not, then of course we'll fall back to the Bisort's theorem and that standard approach. Okay. But so I think we have around 5 minutes left. So maybe I'll just quickly talk about some puzzle or game. What can we do? So I just want to quickly talk about the idea which we mentioned last time about at the very end I talked about how we send bytes, 1 byte of 8 bits, which can represent up to 256 different symbols in binary notation. So, and I also mentioned that we can be more efficient about it. So we can be clever and do a better job. So what can that look like? So that is what I want to talk about. So let's take a simpler example. Let's not have 256 characters because we cannot do that on our paper. But let's say the English alphabet has only 4 letters, okay? A, B, C, and D. Or you have some language which has only 4 letters, A, B, C, and D. So how many bits will you require to send one symbol? So or one character. So how many bits will you require to send one character of this language?
I didn't get the question.
So let's say you have some language which has only 4 characters, A, B, C, and D, and you want to send this information over the internet. So you want to encode these characters as binary numbers and then send them. So how many bits will you require to encode every character?
2 bits.
2 bits, right? Because I can write A as 00, B as 01, C as 10, and D as 1. So whoever is sending the message, they will convert this message into these binary numbers. They will send the binary numbers over the internet, and the receiver will decode the sequence back. So let's say if the receiver gets the message 011110, they know that the sender wanted to say B, D, C, for example. Okay, so that is how somebody can encode and send information and decode. And typically in the literature, these are called symbols. And what we want interested to know is what is the average bits required per symbol. Okay, so in this particular scheme of encoding, the average bits required per symbol is 2, right? So because if you want to send 3 symbols, you require 6 bits.
Yes.
Okay. So now the question is, suppose like just in English language, all the 26 letters don't occur equally frequently, right? Typically vowels occur more frequently than other letters. So in the same way, let us say we know for a fact that the most probable 50% of the times letter A is going to come, 25% of the time letter B is going to come, and C and D are both going to come 12.5%. Okay. So A is the most frequently used character, and B and C, D are used less frequently. So if we know this information, can we do something better? Why are we using two bits for every symbol? If we know that A is going to occur more frequently, maybe we should use less bits for A and more bits for others. Can we do something like that?
So to find the minimum average. Okay. But so we have to represent in binary. So each will have at least like 0, 0, 0, 1 something.
No, but who said you have to use a symbol of length 2? Nobody is forcing you that, right?
But so using a symbol of length 1 may create confusion. For example, if we have 0 and then 0, 1, so and then again a 0, so it may be like A and then 0, 1 may be B, and then we have one more 0, so that may be like C or A B C. It will maybe a confusion.
Yes. So that's a very valid point which Anushka. Suppose we decide, see the sort of logical assumption is that if A is occurring so frequently, let's use only single bit for A. Okay. Let's say we write A as 0. And even B is occurring 25% of the time, so let me write B as 1. And C and D I still have to write as 0, 1 and maybe 1, 0, whatever, doesn't matter. So this is what we call fixed length coding. Because every symbol has the same fixed length of 2. But here what we are doing is called variable length coding, where the length of each symbol is different. But here the problem is, suppose I get 0, 1, 0, 1. Can we figure out what was the message?
No,
So it will be either
because this has multiple interpretations, right? This can either
Can have AB or CC.
Yeah, so many ways. So it can be AB,
or,
it can be
or it can be ADB.
ADB also. So this method will not work. But but you get the idea, right? If we do this, clearly the number of bits we are going to consume is going to come down.
And
Yeah.
maybe if we have three, like this is not related to this, but if we have three digits like 0, 1, 2 in base 3, we can just reduce the length.
Yes, but we don't have that luxury. See, in the physically speaking, in electrical engineering term, you have a wire on which you are sending a voltage, and that can be either 0 or 5 volts. There is nothing in between. So you don't have a third digit available. See,
Sir,
the only
or
problem is the receiving person, there is an ambiguity. But we are free to design this code anyhow we want. So can you be somehow clever and assign the right binary characters for ABCD where this confusion will not occur? Yes, Gaurav?
Sir, I had a completely different idea that instead of compromising on how we send the information, we could probably change how we read it, and then the number of bits could probably be reduced.
What do you mean how we read it?
So suppose if I have a number like say 0, 1, 0.
Okay.
Sir, so first I'll read 0, 1,
Okay.
which corresponds to B, and then I'll take one and then I'll read 1, 0. Like basically the last digit which I'm reading is again used for reading that second digit. So like basically the same digit is used twice.
But maybe see if somebody wants to send A, then they'll send 0, 0, 0, 0. So then I mean there is no way of reusing the previous digit, right? Oh, or okay, what you're saying is in the previous fixed length coding, you want to interpret this as 0, 1, 1, 1, 1, 0.
Yes, sir. Yes, sir.
But
Yes,
the difficulty is some messages may not be able to encode like that.
Okay, sir.
Because see, if the sender wants to send 0, 1 followed by 1, 1, then the same digit is reused. But what if the sender wants to send 0, 1 followed by 0, 1? So I mean, if they want to send BP, then they'll send 0, 1, 0, 1, right? There is no.
Yeah.
Yes, sir.
So then in your scheme, some messages cannot be sent at all. That is what.
Okay, sir. Yes.
Okay. So see here, somehow you can design this mapping in a way where this confusion goes away, then the problem is solved. And let me show one way to do that, and you can have a different way to do that. But for example, let us say I indicate A as 0, okay, B as 1, 0, C as 1, 1, 0, and D as 1, 1, 1, 0, for example. Do you see that this scheme will have no ambiguity? It may not be most optimal for now, but at least the problem of ambiguity is solved, because now if I get this 0, 1, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, 0, 1, 0, 0, 0. Can you figure it out? What was the original message from this? There is no other way to group it, right? There is exactly one way to group it, which will make sense.
If
Any
we
other
see
grouping?
one, we just go to the end 0.
Yeah, correct. But in this process, you can compute what is the average number of bits being transmitted. Maybe it is less than 2, greater than 2, I don't know. But I've just given an example of how you can do the input. So anyway, I'll leave this as an exercise for you and try to see.
But won't this increase the bits per symbol?
What do you mean?
Like now the total bits we are using is.
Let's compute that. So A occurs 50% of the time and it uses 1 bit. So 1 bit is used 50% of the time. So on an average, it is like 0.5 bits are being sent. B has 2 bits and it occurs 25% of the time. So basically, this also has 0.5 bits on average. And same for C and D. So C has 3 bits, which occurs 25% or 12.5% of the time, or that is 1/8 time. So this is 3 by 8, and D has 4 bits, so 4 by 8. So the total average number of bits consumed is the sum of all of these. And how much is that? 1 integer 7 by 8. So it is less than 2. So we have achieved our target. We are using less number of bits compared to the original fixed length coding scheme. This variable length coding scheme can be uniquely decoded as well as it uses less number of bits. The question is, can you do better? This is a very small improvement. What is the maximum improvement that you can get? Okay, so I'll leave you with that question. Okay,
Yes.
that's all. Thank you.
Thank
Thank
you
you,
so much.
sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank
Bye,
you.
sir.
Thank you, sir. Bye.